transfer function, and we made a couple of, no, not yet. Okay, so we have covered till this point. Okay, at the zeros of a system, our transfer function becomes 0, and at the poles of a system, our transfer function becomes infinity. Now let us come to discuss the general form of transfer function. So am I audible, student? Anyone can respond? Am I audible?
Yes, sir.
Okay. General form of transfer function. You see, this is an nth order system, which is described by this linear, nth order linear ordinary differential equation. You write down this equation. This is a linear or linearized ordinary differential equation. And here you see we have only one output y and one input, that is f. We have only one output, that is y, and we have only one input, that is f. Now if we take the Laplace transform and then rearrange, we get this expression for transfer function capital G. If we take the Laplace transform and rearrange, we get this form of the transfer function capital GS. Fine. Now you see in this equation Zi, Z1, Z2 to Z small m, those are zeros. And Pi, that means P1, P2 to Pn, those are poles associated in the polynomial present in the denominator. As I mentioned before, that this transfer function is basically the ratio of two polynomials. One is in the numerator, you see, which includes the zeros, Z1, Z2 to Zm. Another polynomial is present in the denominator, and that includes the poles P1, P2 to Pn. Okay, now this is, you note down this point. Now the order of the denominator, if is greater than the order of the numerator m, then the system is called strictly proper. When the order of the numerator is equal to the order of the denominator, it is called semi-proper. And if the order of the denominator less than the order of the numerator, the corresponding system is called improper. For the first two cases, we also use this term, physically realizable system. For the first two cases, I mean strictly proper and semi-proper cases, we use the term called physically realizable system. The improper systems are not physically realizable. The improper systems are not physically realizable. I'll briefly discuss this issue a little later. Okay. Now let us note down the examples. N is greater than m, that means the order of the denominator polynomial is greater than the order of the numerator polynomial, which is obvious from this example transfer function. And these type of systems are basically lag systems. They have, phase angle which is negative. They have phase lag, in fact. So these type of systems are called lag systems having this transfer function, n greater than m. If n is equal to m, this is called lead lag system. And n is equal to m, we have this type of example for GS, that is tau 1s plus 1 divided by tau 2s plus 1. And these systems are usually called lead lag system. Now here I just want to mention one point. See, if among these tau 1 and tau 2, if tau 1 is greater than tau 2, then it behaves like lead system. If tau 2 is much higher than tau 1, then it behaves as lag system. Okay, I repeat, there are two time constants you see, one is tau 1, another one is tau 2. If tau 1 is much higher than tau 2, then it behaves like lead system. Whereas tau 2 is higher than tau 1, in that case, this system, the corresponding system having this transfer function, behaves like lag system. Okay. Now, if it is lead system, it behaves like improper system. If it is lag system, it behaves like strictly proper system. So whether it is strictly proper or improper, it totally depends on this tau 1 and tau 2 value. And therefore the term we have used here, semi-proper. I repeat the concept. If tau 1 is much higher than tau 2, it behaves like lead system. And it is somewhat like, this improper system. If tau 2 is much higher than tau 1, it behaves like a lag system. And it is somewhat like strictly proper. Okay. Therefore, n equal to m corresponds to semi-proper. Because whether it is proper or improper, it completely depends on the comparative value of tau 1 and tau 2. Now you come to the improper case. If n is less than m, that means we have this type of transfer function. Tau 1 is plus 1 divided by tau 2. It is a lead system. Fine. And we will discuss all these three systems, particularly first two systems in detail. Now you come to draw a couple of remarks, couple of conclusions. For a physically realizable system, n is greater than or equal to m. It is also indicated before. Whenever we have n is greater than or equal to m, it is usually physically realizable system. A system is stable if all poles lie in the left half of S plane. I think you know this second point. A system is said to be stable if all the poles of that system lie in the left half plane of the imaginary axis. We call like this, or left side of the imaginary axis. A system is said to be stable if all the poles lie in the left hand side of the imaginary axis or the left half of S plane. So this is about the pole. Now come to the third point or third remark, that is on the zeros. Zeros does not or do not play any role on stability of a system. Rather, it affects the dynamic response. Zeros do not take part or play any role on the stability of a system. Rather, it affects or they affect the dynamic response of the process. Fine. So these are the three remarks. Now I just want to discuss that realizability, physical realizability part. Yeah. Now you see, I have mentioned before that a system is improper when we have n less than m. Let us see how we can define the physical realizability for this system. It's quite simple. When n is less than m, that means let us consider n equal to 0 and m equal to 1. See, I repeat, we are currently discussing the improper system. We want to also clearly understand what is the meaning of physical realizability of a system. So that's why we are discussing this here. So for the improper system, as I mentioned, n must be less than m. Accordingly, we are considering n equal to 0 and m equal to 1 in a sample case. So if that is the case, then we have this transfer function. You see, gs equal to y bar s divided by m bar s equal to this. Fine. gs equal to y bar s divided by m bar s. So that we are getting b1s plus b0 divided by a0. Now you can write separately here. Y by f equal to this. Y by f equal to this. Now one of your friends asked me before, what is the use of this transfer function. I have given the answer briefly. So here, in fact, we are applying that concept. You see, this is the transfer function. This is the transfer function which is usually reported or which is available to you. Fine. Now, we want to introduce some change in the input variable f. We want to introduce some change in the input variable f, and against that change, we want to observe what is the dynamic response in terms of y. I repeat, the transfer function for a particular process is known or it is available to you. Like this is a transfer function, you see. Now, what is asked? You introduce some change in input variable. Some change means, suppose if you consider a liquid level system, we have considered several times. We have one input, that is Fi. We have one output, that is capital F, for a liquid tank system. Now suddenly there is a change in Fi like this, step change. Against this change, what type of response we can have in the liquid height? That we can observe from this analysis. So accordingly, we are proceeding. You see, this is the transfer function. Now we are introducing some step change in F. So here, let us consider a unit step change. That means F bar is equal to 1 by S. Now against this unit step change, what should be the response in terms of Y? That we want to find out. So accordingly, you see, I have written the equation. Substituting F bar is equal to 1 by S. Now, if we want to know the dynamic response in terms of Y, we need to take the inverse of Laplace transform. You see, the inverse of Laplace transform is taken and we get the expression for Y in time domain. What is this delta t? Anyone can tell? What is delta?
The delta function, the impulse function.
Yes, impulse function. So what is the value for this? Infinity. Fine. That
Yes.
means you are understanding this is not physically realizable. Y value is having this infinite value. That means it is not physically realizable. So that's why the term I have mentioned for improper system, I mean the improper systems are not physically realizable. This is the explanation. But if you go for the semi-proper or strictly proper systems, you will have certain value. Finite value you will have. Clear? So that's why I have mentioned the improper systems are physically not realizable. Fine. Let us come back to our earlier discussion. Yes. Now, based on this concept, we will go for stability analysis. Based on this discussion, we'll go for stability analysis. And at first, we'll go for qualitative analysis. The next discussion is stability analysis, and it is qualitative analysis, not quantitative analysis. So equation 1 is quite obvious. Transfer function is equal to output divided by input in Laplace domain. From that only we get equation 1. Okay. It is also mentioned before that this transfer function is nothing but the ratio of two polynomials. And here they are represented by capital Q divided by capital P. This example also I mentioned before, tau 1s plus 1 divided by tau 2s plus 1. Okay. Now additionally sometimes happens that the input is again the ratio of two polynomials, Rs divided by Qs. It also sometimes happens that the forcing function or input variable small f, that is the ratio of again two polynomials in S, and that we are representing by small r divided by small q. Here I have also given one example for this. Suppose our input variable is a ramp function at. So it means it is a divided by a square. So it is a ratio of two polynomials. Okay. Although there is no polynomial in the numerator, but we can have sometimes. Anyway, we are not going to also consider this. Just write the general form. In equation 1, if we substitute f equal to small r divided by small q, we get this expression for y. Okay. If we substitute in place of small f equal to small r divided by small q, we finally get this expression. Fine. Yeah. Now let us start the stability analysis. In fact, qualitative analysis. So yeah, we are not in fact going to consider this r divided by q, just for show the generalized equation I have mentioned this. Now let us come to this form. We are going to use this transfer function for qualitative stability analysis with the following general form. You see equation 2. We will perform our qualitative stability analysis with equation 2. Fine. So I repeat, we are going to perform the qualitative stability analysis with equation 2. Yeah, it looks apparently quite complicated equation. Although at the end of this discussion, you will see that it's quite easy to understand. It's not so difficult. Actually, we have considered this equation 2 with all types of poles, like positive pole, negative pole, complex conjugate pole, pole at the origin. All the different types of poles are considered or accumulated in equation 2. That's why apparently it looks complicated. Okay. all types of poles are considered in equation 1, starting from the negative pole, positive pole, complex pole, pole at the origin. Fine. So let us start then. So if we want to find the, if we take the inverse of Laplace transform, in that case we need to go for partial fraction expansion of equation 2, which is shown here. Before going to take the inverse of Laplace transform of equation 2, we need to do this partial fraction expansion as shown here. This I think you all know. You all know this partial fraction expansion. Which is shown here for equation 2. Okay. Now let us come to the graphical representation of all the different types of poles. So we have pole P1, P2, P3, P4, P4 star, P5. 5 different types of poles are shown here. P1, P2, P3, P4, P4 star, P5. Fine. Now we want to graphically represent the S-plane. This is our real axis, x-axis, and this is our imaginary axis. Okay. Now, if you remember the 5 poles, P1 to P5, you see P1 is negative pole, P2 is positive pole. Okay. P3 is both positive and negative. P4, P4 star, they are complex poles, and P5 is present at the origin. Okay. So as I mentioned before, all kinds of poles are accumulated in equation 2. That is quite obvious from this graphical representation. P1 is positive, P1 is negative pole, P2 is positive pole. P3, we consider both positive and negative. P4, P4 star, they are complex conjugate poles. And P5 is the pole which is present at the origin. With this consideration, we'll proceed further for stability analysis. Okay, with this graphical representation, we want to proceed further to perform the stability analysis. Okay. Now here, this is the S-plane, and we are considering S is basically A plus JB. Now we consider this first case, real distinct poles. We'll consider the different cases one by one based on our transfer function presented in equation 2, followed by its partial fraction expansion. We will consider the partial fraction expansion form of equation 2 to discuss different types of poles and the corresponding stability. So let us start with real distinct poles. So you see the GS expression, what we have presented in general form, that is here, presented with only two distinct poles. One is P1, another one is P2. Okay, we have reduced the expression for GS presented before to consider only the two distinct poles, they are P1 and P2. In the plot also it is shown that P1 and P2 are distinct. In fact, P1 is shown in the negative side of the imaginary axis and P2 is shown in the positive side of the imaginary axis. You see, P1 is here in the negative side of the imaginary axis and P2 we have considered in the positive side of the imaginary axis. So it clearly indicates that P1 and P2 are distinct and they are present on the real axis. So they are real. They are not imaginary at all. Now if you take the inverse of Laplace transform, we get this form. So it's not Laplace domain, it is time domain. You just correct it. So this is actually in time domain. Okay, this is in Laplace domain. Now you consider first case. Suppose P1 is less than 0 as it is shown in the plot. Suppose P1 is less than 0 as shown in the plot. What does it mean? C1e P1t exponential P1t. It decays exponentially to 0 as t tends to infinity. So initially our time is 0. Then as we proceed, this time t increases towards infinity. Initially, we start our process or operation from time t equal to 0. As we move forward, our t increases, and that's why we have considered t tends to infinity. So if P1 is negative and t is going towards infinity, that means this exponential term decays exponentially. Okay, so it is towards going to 0. But if we consider the another term, that is C2 exponential P2t with P2 greater than 0, then the second term grows exponentially to infinity as t tends to infinity. So this first term is moving towards 0 and our second term is moving towards infinity. So if we just add them, it means we are moving towards infinity with time. Okay. And graphical representation, we are moving towards 0 means it is stable system. And we are going towards infinity means it is unstable system. We are going towards 0 means the system is stable, and we are moving towards infinity means the system is unstable. So this is the graphical representation. Okay. Now, this is a graphical representation when we consider t tends to infinity, and our P1 is negative side, P2 is positive side. So in brief, we can write this. When two poles lie in the negative side or left hand side of the imaginary axis, system is stable. If two poles are positive, system is unstable. If one positive, one negative, it is also unstable. So we can say that for a system, even one pole is present in the right half side or right half plane, the corresponding system is unstable. Even a single pole or one pole is present in the right half side or right hand side, then also the system is unstable. So this is our conclusion for two distinct real poles. This is our conclusion for two distinct real poles. Now come to multiple real poles. In the second case, we are going to consider multiple real poles. So that's why if you recall the graphical representation, there are two P3 we have considered. One is in the positive side, another one is in the negative side. Okay, multiple real poles. So accordingly, we have reduced the transfer function to this form from the generalized form. This is a reduced representation of the reduced transfer function from its general form shown before. And then we have taken inverse of Laplace transform and we get this form. If we take the inverse of Laplace transform, we get this form. Okay. Now you see what I have written. We have considered separately two terms. One is within the third bracket, that is first term, and the rest term is exponential term. We are considering separately two terms. One is presented within the third bracket, and the second rest term is the exponential term. Okay. Now this term is growing towards infinity with time. The terms which are presented within the third bracket, that consolidated term grows towards infinity with time. So the stability is depending on, rest we want to discuss the exponential term for stability analysis. So for this exponential term, e to the power p3t, if this is the case, p3 greater than 0, in that case exponential p3t tends to infinity as t tends to infinity. So let us discuss this exponential term, because this one we already fixed. So for the exponential term, if p3 greater than 0, then this exponential term grows towards infinity as t tends to infinity. So what is the multiplication of these two terms? It is growing towards infinity. Okay. This is growing towards infinity. This one is also growing towards infinity. So overall, it is growing towards infinity. That means the system is unstable. It means the system is unstable. In another case, we are considering P3 less than 0. In this case, the system is stable. If P3 less than 0, in this case, the system is stable. And in the third case, we are considering P3 equal to 0. So in this case also, the overall system is growing towards infinity, and thus it is unstable. In the third case, we are considering P3 equal to 0. P3 equals 0. With this, the overall system grows towards infinity. That means the system is again unstable. Anyone has any remark or comment on this second case? Student? Anyone wants to include something? No. Okay, I just want to mention here, you see here I have written grows towards infinity. Okay, it is true if all the coefficients are positive. I have written for this third bracket, you see, it grows towards infinity with time. It is only possible, it basically depends on the sign of these coefficients, C31, C32, C33. Okay. So I think you are understanding the concept. It may not grow towards infinity if the coefficients are like that, in fact. If you are negative and it is moving towards 0, in fact. Okay. So anyway, positive and negative sign you have to consider for the coefficient, and accordingly you need to make this comment. That you can easily understand from the mathematical expression directly. Okay, now come to this third case. Complex conjugate poles. In the third case, we are considering complex conjugate poles. Accordingly, our expression for transfer function is reduced to this form. Okay. For the complex conjugate poles, our transfer function is reduced to this form. If you recall the graphical representation, there I have shown there are two poles P4 and P4 star, and they are complex poles, conjugate poles. Now we are considering P4 equal to alpha plus J beta, and P4 star we are considering alpha minus J beta. So alpha is the real part and beta is the imaginary part. In this example, we are considering alpha is the real part and beta is the imaginary part. So these poles are present in the S plane or our graphical representation which we have shown before. Now for this, if we want to take the inverse of Laplace transform, we get this type of expression. If we take the inverse of Laplace transform, we get this type of expression. Final expression, you see something within third bracket, it is certain constant term, then exponential term, then sine function. If we take the inverse of Laplace transform, we finally get some constant which is written within the third bracket multiplied by exponential term, then one sine function. If we take the inverse of Laplace transform, we get finally this form. This exponential term depends on alpha, and this is indicating the periodic oscillation. Okay. Now let us consider the effects of real part. You see the first case. If alpha is greater than 0, then e to the power alpha t tends to infinity as t tends to infinity. That is quite obvious. It means the entire term, this one, is growing with increasing amplitude. If alpha is greater than 0, e to the power alpha t tends to infinity as t tends to infinity. That means the entire right hand term indicates growing oscillation with increasing amplitude, which is also graphically shown in the right hand side. So it clearly indicates that system is unstable system. Can anyone tell what will happen if alpha less than 0? Anyone can give the answer. If alpha less than 0, what will happen?
It will decay over time. The oscillatory function.
Oscillatory function?
Will decay over time. It will flatten out to straight line.
Yeah. Yeah. So it is stable or unstable?
Stable.
Stable system. Correct. If alpha is less than 0, we will have oscillation with decreasing amplitude. In the similar fashion, case 2 is shown. If alpha less than 0, then we will have oscillation with decreasing amplitude. Which is also shown graphically in the right side. So what will happen if alpha is equal to 0? Do you have the answer? If alpha is equal to 0, what is going to happen?
The amplitude of the oscillations will remain the same.
Tell.
The height of the oscillations will remain the same throughout time.
Yeah, so it is what type of oscillation?
Stable.
It is stable. So you are saying it will be sinusoidal wave, no?
Yes, sir. Yes, sir.
Yes, like this, I think you were saying. Oscillations with constant amplitude. Oscillation with constant amplitude. So what do you want to say? This is stable or unstable or what? What do you think?
It feels stable to me. Like it does not increase to infinity at any point, so it feels stable.
But it is also not decreasing, no? You were saying it is not increasing, but one can say that it is also not decreasing. Yeah. So in chemical engineering, we call this as marginally stable. This is, I think, the suitable term. Marginally stable. See, this process control or control system is a multidisciplinary subject. It is taught in many disciplines, including electronics, electrical, mechanical, aerospace, cryogenic. Okay, they also have this control system subject. Like if you think about the control of an aircraft, okay, or a missile, they have very strong and accurate control system, which is taught in aerospace engineering. But they consider it is not stable. Okay, because they need very rigorous, very accurate control action. But in chemical engineering, we do not need so much accuracy. Only difference is that in chemical engineering we have very large system, but they have very small system. They have mostly 1-2 variables, but we have hundreds and hundreds variables. Like if you consider one refinery distillation column, Forget about a complete refinery plant. You just consider one refinery column. It may have 200 to 300 state variables. Just one multi-component distillation column, 200 state variables. Forget about the complete refinery plant. But if you think about the missile, which is dealt in other disciplines, including the nuclear science or maybe sometimes in aerospace engineering, they have very limited state variables, 1, 2, 3 state variables. So I repeat, we have the heavy process, large process, but we do not need so much accuracy. If the composition decreases or increases 10 to the power minus 5, it hardly matters. But for them, they need very, very accurate action. But their systems are small. And that's why we are considering it marginally stable system, but in their case, it's not stable at all. Okay. So this one is another one, fourth one, poles at the origin. And our transfer function is reduced to this form, C5 divided by S minus P5. Our transfer function is reduced to C5 divided by S minus P5. And in the graphical representation, I have shown that P5 is located at the origin. So naturally, our P5 is 0. Accordingly, C5 divided by S is our final transfer function. Now, question is how it behaves. So for that, we need to take inverse of Laplace transform, from which we get C5 constant. So this is about the qualitative analysis. Any question, anyone? If you have any question, you can ask me. Okay. Since you do not have any question, I have one question. Is this equation correctly written? You can check. You just check this equation. Yt equal to C5 Ft I have written. Is it correctly written? Anyone can give the answer. Is this expression correctly written? Or it is wrong expression? Okay, you try to find the mistake. This is a wrong information, wrong expression. You just correct it. Okay. This last expression is not correct. So where is the mistake you find and correct the equation? Okay, you take 5 minutes leave, 5 minutes break, then we will again come back. Let us go for 5 minute break and we'll again come back. Okay, let us come back. Yeah. So next our new topic is dynamics of first order systems. Our next topic is the dynamic study of first order system. In fact, in the next few classes, we'll study the dynamics of first order, second order, third order, higher order systems. And let us start from first order system. The definition of first order system is written, you see. A first order system is one whose output y is modeled by a first order differential equation. So a first order differential equation in terms of y represents a first order system. Accordingly, we have taken one first order ordinary differential equation, you see, as a linear or linearized system. Accordingly, we have taken a linear or linearized first order ordinary differential equation. Here y is the output, f is the input or forcing function, t is the independent variable, and a0, a1, b, these are constants. Y is the output, f is the input, a0, a1, and b, these are constants. Okay. Both y and f, they are deviation variable. Both y and f, they are deviation variables. Now with this linear or linearized ordinary differential equation, we will consider two cases. In the first case, we are considering a0 not is equal to 0. I repeat, for this dynamic linear system, we will consider two cases. In the first case, we are considering a0 not is equal to 0. So accordingly, our ordinary differential equation becomes this. Accordingly, our ordinary differential equation gives this form. Okay. Now we can further write this equation with tau p and kp. This equation is rewritten with including tau p and kp terms. This equation is further written in terms of tau p and kp terms. So here tau p is the time constant of the process and its unit is all the times time. Tau p in this equation is basically the time constant of the process. It has the unit time. Another one is Kp, that is steady state gain. Kp is the steady state or static gain. Can anyone tell why it is called a steady state gain? Anyone can give the answer why Kp is called steady state gain?
So because at steady state dy by dt will be 0 and so y will be kp into f of t.
Correct.
That's why.
Yeah. What's your roll number?
19ch 30034.
Yes. At steady state, this dy dt is 0 basically. Okay. At steady state, this dy dt is equal to 0. If so, Kp equal to y by f. So Kp equal to basically del y by del f, because y is deviation variable. Now, delta output divided by delta input, this is a definition of gain. Okay, gain is basically change in output divided by change in input. That's why the term gain. And steady state or static term is present here because it is possible to get only when dy dt equal to 0. That's why steady state or static term is there. Okay. Now if we take the Laplace transform, then you see we get this transfer function. If we take the Laplace transform and rearrange, we get this form. This is called first order lag system. I have also indicated before, this is a lag system. So we get the transfer function when a naught not is equal to 0. This is the first case. And in the second case, we will consider a naught equal to 0. Then our linear first order ordinary differential equation yields this form. If we consider a naught equal to 0, then our first order ordinary differential equation yields this form. A1 dy dt equal to b into ft. Okay. Now, if we take the Laplace transform, we get this. So here you see Kp prime is the gain. Here Kp prime is the gain. Is there any mistake in this equation? Student? Yes.
A1 on the top, but it's getting paid.
Sir, the denominator will be A1.
Yes. B divided by A1. Ft. This one. Yes, you correctly write it. B divided by A1 into Ft. So it must be B divided by A1. Okay. Now our transfer function we have written in this form. If we in Laplace domain, if we take the Laplace transform, we get the transfer function GS in this form. So this is purely capacitive process. Or pure integrated process. Okay, so there are two cases. In one case we got we consider A naught not is equal to 0. In another case we consider A naught equal to 0 and we get one is first order lag system, another one is pure integrated system. Let us take one example to discuss this issue. Let us discuss this concept with a couple of examples. So this is your first example. We have considered a simple liquid tank system. In fact, this system we have also considered before. Okay, so here we are considering one resistance term, that is R, in the outlet section. Is this expression fine? F equal to H by R. Did you have any such expression in other subjects? Chemical engineering subject? Student? I have written this equation. Did you have any similar kind of equation or expression in any other chemical engineering subject? What you got in your heat transfer course?
Conductive heat transfer.
Yes.
Del T by R you got, no?
Yes, sir.
Yes. In a similar fashion it is written here. Rate of heat transfer is equal to del T divided by R. Anyway, so this is our model. And we have substituted simply in place of F, H by R. Outlet flow rate F is replaced by H by R here. Then you see, we can easily write the expression in this form. Can anyone tell what is the unit of tau P? In this example system, what is the unit of tau P?
Second.
So time.
Yes, time. And what is the unit of Kp? What is the unit of Kp?
Length.
So second square by kg.
Second square. Oh, okay. If you are considering, I think kg per. This F is volumetric flow rate. This F is volumetric flow rate. You see this equation, meter square into meter per second. So meter cube per second, same unit with F. F is volumetric flow rate, not mass flow rate.
Meter will be the unit of K.
Meter. How you are getting meter? You see, you get the unit from here only. This is meter cube per second. This is meter.
T by meter square.
Yes. Time per meter square. So you just remember the unit of tau p is always fixed. That is the unit of time. But unit of kp is not fixed. It varies from, system to system. Okay. Unit of tau p is always the unit of time. What time unit we are using here? If it is a meter cube per minute for volumetric flow rate, so it may be minute. But the unit of kp is not fixed. It varies from system to system. Okay. So we got this transfer function. We got this transfer function. So here our time constant is this storage capacitance multiplied by resistance to flow. It is the storage capacitance of mass, cross sectional area, this one. Time constant tau p is basically cross sectional area into resistance, and cross sectional area basically is the indicative quantity for our storage capacity. Okay.
Sir, can you scroll up?
This one?
Yes, sir.
Can I move now?
Yes, sir.
Yeah. Now you do this problem. You find the transfer function and let me know the expression for tau p and kp. Okay. Now you find the transfer function for the example 2 and let me know the expression for tau p and kp. I just want to mention here, this is the steam which is going through the coil, and steam temperature is T suffix St. I repeat, steam is going through this coil, which is basically giving Q heat to the container liquid, and the temperature of this steam you consider as T suffix St, steam, St. Go ahead. Let me know the transfer function Gs and the expression for Kp and tau p. Anyone got? Anyone? No.
So the transfer function is UA, where A is the area for heat transfer divided by SV rho Cp plus UA.
Good. What's your roll number?
19CH 10047.
You check now?
Yes, sir. This is what I'm getting.
So here static gain is 1. So you see the expressions for Kp and tau p. Here storage capacitance is corresponding to the storage of thermal energy V rho Cp, and heat transfer resistance, I think you all know, 1 by U. I mentioned before that Q equal to del T by R equal to UA del T. You just proceed like this way. If you forget this, in heat transfer we consider capital Q equal to UA delta T. In heat transfer we consider Q, capital Q equal to UA delta T, and that is equal to again delta T by R, capital R, which is resistance. So Q equal to UA delta T equal to delta T by R. So R is obviously 1 by UA. Resistance R is thus equal to 1 by UA. Fine. So accordingly, this is the resistance to heat flow, 1 by UA. Okay. Let us come to another example. That is pure integrator system. Let us come to another example, that is pure integrator system. This one is the example, you see. Here we have a constant displacement pump in the outlet section. In this example system, we have a pump which delivers constant outlet flow rate capital F. Okay, that's why I have written here constant displacement pump. That means it delivers a fixed quantity of stream. It delivers a fixed quantity of F, outlet flow rate. So that's why F is constant. Fixed quantity of liquid is delivered through this constant displacement pump. That means F is constant. That's why in terms of deviation variables, it is like this. Now you see this is the transfer function. If we take the Laplace transform, we get this transfer function, which is Kp prime by S. And you know that 1 by S is basically the transfer function of an integrator. Okay. Now this is a transfer function for a pure integrator system, Kp prime by S. There is no time constant in fact. Now let us just go for the dynamic response. In the title, I have mentioned the dynamic response of first order system. Let us move towards in that direction. I repeat, I have mentioned in the title that dynamic response of first order system. So let us gradually move towards studying the dynamic response. Let us start with this purely integrated system. So we can easily write from this equation this form. We can easily write from this developed transfer function model this form of equation. Okay. Now we are just considering a unit step change in the input stream, that is Fi. We are introducing a unit step change in the inlet stream Fi prime. It is also graphically represented in the right hand side. It is also graphically represented in the right hand side, you see. Okay. Now let us substitute in this equation. In place of Fi prime, we are writing 1 by S. So unit step change means this is the representation. If you write in time domain, it is 1. If you write in Laplace domain, it is 1 by S. I think you know this. Unit step change means in time domain, you write like Ft equal to 1. But if you write in Laplace domain, it is F bar S equal to 1 by S. Okay. So you see, this is the equation. If you further take the inverse of Laplace transform, Fine. Now graphical representation, you see. This is the graphical representation of y with reference to time when the process is subjected to a unit step change in input variable. This is the dynamic response of y when the process is subjected to a unit step change in input variable f. So you note down these two remarks. It is called pure integrator because as mentioned, it is an integrator between input and output. Are you understanding the second point? It is non-self-regulating system. Got this second point, student? You come to this point then. Come to this schematic. If I increase Fi, this liquid height will consistently increase because this outlet flow rate F is fixed. Got the point? If we increase the Fi, this liquid height will consistently increase as shown in the dynamic response plot. This is because our outlet flow rate is constant. So we will not achieve any new steady state in terms of H. I repeat, if we increase Fi, this liquid height will consistently increase. It will not stop anywhere and reach a new steady state because this outlet flow rate F is constant. Okay, so this is a reason. Do you have any question? If not, we will stop here. Any question, anyone? No. Okay, thank you then.